And team, thank you so much for asking me to talk about AI and point of care in obstetric ultrasound. I'll talk to you a little bit about some of the concepts and future directions that we and others have been working on. My name is Aris Papageorgiou. I'm a professor of fetal medicine at the University of Oxford. I also work at St. George's Hospital in London, and my Twitter handle is on the screen in front of you. If you want to follow me, I'll be very happy. By way of declaration of interest, I do need to say that I'm a co-founder of a company called Intelligent Ultrasound, now part of GE Healthcare, who develop AI to improve ultrasound. I have other declarations on this screen in front of you, but they're not relevant to this particular presentation. Now, what I wanted to start with is a WHO recommendation on antenatal care for a positive pregnancy outcome. And what the WHO recommends is that all women around the world should have an ultrasound examination in order to, at the very least, check for cardiac activity in pregnancy, fetal number, chorionicity if you have a multiple pregnancy, estimate the gestational age, and we'll talk a little bit about that today, fetal size, and some basic obstetric imaging for abnormalities, as well as placental appearance and location. The reality, however, is that it is estimated that around 40 and perhaps 50% of women around the world still do not have antenatal ultrasound at all during pregnancy. And one of the things that we and others have been working on is trying to see if we could help bring that to improve that situation. Now, in order to improve, it's important to understand what is difficult, and I like this paper very much from Sachita Shah because it's still really relevant. The two main barriers for ultrasound are equipment factors in black on the screen and human factors in red on the screen. So a lack of ultrasound equipment is there but isn't working, or is there and is broken. And on the other side, a lack of trained staff and a lack of training opportunities are both important. Now, to be fair to our industrial colleagues, they have been working hard at trying to create low-cost ultrasound, and there are a number of options available to us. This is just some of them, by no means an exhaustive list, but there are now lower-cost ultrasound devices, wireless, wired, and often handheld devices in order to reduce the cost. However, the problem of having trained people still evades us. And this is where we come to the concept of whether one could use artificial intelligence to try to improve that situation. So AI is commonly used in real-world settings, for example, in self-driving cars. In this example here, the AI has been trained using thousands and thousands of natural images to do two things. The system is doing instant segmentation. Segmentation means it draws around particular images that it's seeing in front of it. It's drawing around the bus, around the car, around the pedestrian. And the second thing it's doing, it's labeling each of the images. It's saying this is a bicycle, this is a car, this is a truck, etc. So these two principles that come from computer vision, saying this is what I see in front of me, and this is the outline what I see in front of me, are very important in, for example, self-driving cars, where you don't want the car to run over a pedestrian, and you also need the car to know where the pedestrian ends so that it's not run over. Can we apply these instruments and these principles to obstetric ultrasound? And the answer is yes. So here we have a very basic obstetric ultrasound sweep. It's going to move from the maternal symphysis pubis up to the top of the uterus and do a sort of T-shaped sweep. This is a sweep that we describe in the paper that you see below. And what we see here is that the system labels the head, the amniotic fluid, the spine, placenta, heart, and others. And what this helps us with, and it's doing here a very similar job to what that previous image was showing us, what it's doing is instant segmentation. So it's drawing around the image. It's drawing in bounding boxes here rather than discretely drawing around the image. And it's also labeling the different parts of the baby. And this can be helpful because if you marry that up with knowledge of the probe motion, you can surmise in this example that the baby was cephalic because the first thing you saw was the head. You also know that the amniotic fluid was normal. You also can see that the placenta was high because it was right at the end of that sweep. So using these principles, you can start developing point-of-care ultrasound devices, for example, for the detection of breach. And here in this particular paper, we use 330 or so cases, half cephalic, half breech. And what we see is that the system accurately detects breech at 97% with very, very few false positives. And what's interesting is you can look at the failures too. You can look at the individual failures. There are not many. And often there's an explainable reason for the failures. For example, a calcified fibroid in the lower uterine segment that is misinterpreted as a head in a breech baby. or a baby that's kind of transverse. It's neither properly breech nor properly cephalic. So some of those failures we learn from, and then we can improve the system as we go to more sophisticated learning algorithms. So this is just one example of how point-of-care ultrasound can be used, and then that can be used in low-income settings, for example, where the difference between breech and cephalic is very important in deciding on the place of delivery. But you can then reverse innovate, if you like, and bring those tools into, for example, the system in the UK, where there are currently studies underway to offer a brief obstetric scan for everybody near term in order to reduce the incidence of undetected breech. A second example I wanted to give you today is using AI for gestational age assessment. Now, gestational age assessment is usually done by last menstrual period or by CRL, but in a lot of settings, women don't remember their LMP and they don't come for a CRL. And in these settings, we estimate gestational age based on biometry. The way we do that is we measure the head, the abdomen, the femur, and we put the baby on the 50th percentile, right? So that's how we then estimate the gestational age in a woman who comes at 28 or so weeks. We measure the baby measures 28 weeks and 2 days in size, and we assume that the baby is an average size and plot it in the middle of that range. Now, this approach has three major limitations. The first limitation is that babies that are small for gestational age will be underestimated in gestation, and babies that are large for gestational age will be overestimated in gestation. So there's an intrinsic fallacy in putting the baby on the 50th percentile. The second disadvantage is that the range of normal growth is very wide in the third trimester, so the accuracy of the method is very poor. And the third disadvantage is that it ignores biological variability, right? So it assumes that every baby is the same size at 28 weeks and 2 days, when we know that's not the case. So with colleagues, we decided to use a different concept. You may have seen apps like these. They're quite fun. You take a picture of someone, it tells you their age in years. And we thought, well, is it possible to do the same in the fetus? Is it possible to estimate the gestational age based on the image alone? So here we have two images. They're the same size. There's no measurement there. Can we tell which one of these is 19 weeks and which one is 33 weeks? Those of you who do ultrasound on the call will know that the one on the left is 19 weeks, the one on the right is 33 weeks. And the reason for that, the reason you know that, is you can see the images look different. There's intrinsic variation in the ability to, in the formation of the brain. You can see gyrations on the right-hand side that you don't see on the left. That comes with your experience, and you can teach computers to recognize that. Because if I asked you the difference between a head at 19 weeks and another head at 19 and 3, you probably would find it more difficult. But if you train a computer algorithm with millions of images or hundreds and thousands of images, and the computer algorithm remembers all of those variations in image, maybe it can do a better job. And this is what it does. This is an algorithm trained on hundreds of thousands of images of head, abdomen, and femur length images in babies where we know for certain the gestational age because they had a previous CRL. On the y-axis is the estimated gestational age based on the imaging alone, so no measurement at all. On the x-axis is the ground truth, the estimation of the gestational age based on previous CRL, on the CRL that this woman here had many weeks ago, plus the elapsed time. And what you can see is a high degree of accuracy between the estimation of gestational age based on imaging only and the estimation of gestational age based on ground truth. So this is very important, and this is external validation, meaning we used 94,000 images that the model had not previously seen, so completely new images. Let me just show you an example. The actual gestational age on this picture is 12 weeks and 5 days. We know that from the CRL. And the system is going to estimate the gestational age. It's going to come up here on the left-hand side. So we start the scan, and after a few seconds, the system recognizes that this baby is 12 weeks and 4 days with a confidence interval of 12 plus 1 to 13 plus 0 based purely on that imaging that it saw. It didn't measure anything. It just looked at the baby. And here's another one, not quite as clear image, and you can see immediately the estimation comes up there. It's very accurate compared to the CRL here on the left-hand side. You can see also that it doesn't need to see the whole baby in this particular instance. It was just looking at the head because that's where the image happened to start. We're not the only group that have done this. I'm really sorry I forgot to add the citation on this paper. This paper is important. It is from Stringer, and it's appeared in JAMA in 2024. If you put Stringer JAMA 2024 into PubMed, you will find it. Use a very similar approach to ground truth gestational age using CRL and then image analysis. And on the left panel here is the gestational age using the AI device. On the right-hand side is the gestational age based on reference standard, which is fetal measurement. And you can see that the error rates are essentially very, very similar. So with AI, you can do as well as you would with biometry. And what you do is much better than what is currently the standard of care in many settings, which is LMP. You can see the variability of LMP on the right and the index test, the AI system on the left. And you can see how much better that AI system does. So this is real world stuff. We are one of the companies that have devices in the market right now. When I say in the market, they're part of trials. They're not yet regulatory approved. And these are in a video here from Ghana. So the midwife has been trained to do blind sweeps. On the device there at the back, there's a little cartoon here that tells the midwife how to move the probe. And also, if the probe is not having enough visualization, it prompts the user to apply more pressure. And then the operator just does these blind sweeps. If you look, she's not even looking at the screen. The screen is available there, but she's mostly just looking at her hand, undertaking those sweeps, making sure that she's in keeping with where the machine tells her to be. And in principle, you could even have the system without a screen of the baby. And you could do that in settings, for example, where you want to blind operators. I'll just move forward here a little bit. So what happens at the end then is the gestational age is seen, and you can see everyone very excited that it worked and estimate their gestational age. And this is important stuff because knowing the gestation of a baby is really a crucial factor in management of any pregnancy. And also, if you look at these data, these are data on population attributable risks for stillbirths. And you can see that there are risk factors such as maternal age, malaria, overweight, and obesity. But the biggest risk factor is post-term pregnancy. And a lot of these post-term pregnancies occur purely because gestational age is unknown. So there is a real potential here to improve care in many settings. And of course, we are developing these point-of-care devices for low-income settings. But as I said before, many of them are really applicable in high-income settings too, in particular populations or in community settings. So I have a wish list for AI-enabled ultrasound. I want it to be clinically robust and to lead to risk stratification. I want it in the very first instance to do at least these things: estimate viability, gestational age, twin pregnancy, detect breach in the third trimester and placental location in the third trimester, and also eventually estimate some sort of way the fetal size, either with biometry or automatically, and fluid. My wish list is that this should be easy to obtain by a variety of healthcare workers with minimum training. And my wish list is that needs to be integrated with clinical information. So clinical information, imaging information need to work together. So for example, a breech pregnancy at 20 weeks is of no relevance. A placenta previa at 16 weeks is of no relevance. So that basic clinical information of gestation needs to be taken into account whenever we make judgments around what we should do with imaging information. Just before I summarize, I wanted to highlight that these POCUS systems are intended not to replace high-quality ultrasound, but to replace no ultrasound, be that in low-income settings or underserved regions, in remote settings in Australia or Sweden or anywhere else, in maternity deserts in the USA, as well as in centers in Africa where no ultrasound is available. It is not intended to replace high-quality ultrasound, which we always advocate for. But by replacing nothing, I think we can make big inroads. AI then, as a summary, is a prominent source of innovation. Deep learning is really good at image recognition. We've shown you today some automated basic point-of-care ultrasound, and it is becoming a reality. So we have devices now in 62 centers all over Africa as part of trials. The potential for impact on clinical outcomes is very large, so large potential, but the truth is it has yet to be proven. And finally, I think in this field, we are leading the way in obstetrics, and there are a lot of opportunities for point-of-care ultrasound outside obstetrics that are being informed by the advances that we are making. So thank you very much once more, and thank you so much for the invitation to speak on this really interesting course. Asma team, I really look forward to hearing more about point-of-care ultrasound and look forward to our discussion. Thank you.